Hello dear students, welcome back to pen and paper chemistry, and I hope you have all got your pen and notebook ready so that we can continue with the topic of amines and you can take down some notes for reference in the future as well. Today's topic is structure of amines. This is part 2 of the video series on amines. Talking about the structure of amines, we will correlate it to the structure of ammonia, because in the previous video we have seen that amines are nothing but derivatives of ammonia, right? So nitrogen, let's start with the electronic configuration of nitrogen. 1s2, 2s2, 2p3. Following the Hund's rule of maximum multiplicity, the electronic configuration would be 2s and each of the p orbitals having an unpaired electron. It undergoes sp3 hybridization. Now all these words, if they are sounding a bit alien or unknown, then we have a separate series of videos on hybridization. I would advise you to go through those set of videos where we have dealt with sp3, sp2 and sp hybridization in great detail. So when it undergoes sp3 hybridization, the structure that we have is a tetrahedral one. But remember, we have a lone pair of electrons over here, and a lone pair bond pair repulsion is greater than bond pair repulsion. Yes, all this has been explained under VSEPR theory, VSEPR theory, on the channel as a separate video. A quick glance through it: methane, ammonia, water. Methane also has sp3 hybridization just like ammonia and water. Methane has no lone pair of electrons on the carbon. Ammonia has a lone pair of electrons on nitrogen. Water has two lone pair of electrons on oxygen, because of which, according to the VSEPR theory, there are only bond pair of electrons over here, where all electrons are used up in bonding. So we have 4 bond pairs. It has a regular geometry wherein the bond angle is 109 degrees 28 minutes. You talk about ammonia, there's a lone pair of electrons. Lone pair of electrons is very possessive about its nucleus, so it repels the bond pairs. The bond pairs, they do repel each other, but not to such a great extent as the lone pairs repel the bond pairs. So we say over here, the lone pair bond pair repulsion in the case of ammonia is greater than bond pair repulsion, not just in the case of ammonia, but any compound having a lone pair of electron. In the case of ammonia, because of this lone pair bond pair repulsion, the structure that it acquires is pyramidal. This bond angle, because the bonds are pushed closer to each other by this lone pair of electron, so what happens over here is the bond angle reduces and it shows a bond angle of 107 degrees. The shape now becomes pyramidal. In the case of water, due to two lone pair of electrons, there is further repulsion. So what is happening is this lone pair of electron is not just fighting with the bond pairs, it is also fighting with the second lone pair. So they are battling with each other for the attention of the nucleus, with the result the lone pair repulsion being the strongest compared to lone pair bond pair and bond pair repulsion. Water acquires a V shape. It should be tetrahedral according to the hybridization, but it acquires a V shape. The bond angle is 104.5 degrees. Remember all this, you may find it useful later on. So the same thing applies in the case of amines as well. So there is lone pair bond pair repulsion. The bond angle should be approximately 107 degrees. But what you have to remember is, when we are talking about ammonia, all the atoms which are attached to the ammonia, to the nitrogen molecule, are actually small hydrogen atoms. Whereas in the case of amines, this hydrogen is now replaced by a bulkier group. So for example, I could have a CH3 group, in which case this is carbon. Let me try and expand it and show it to you. So here it is CH3. Now if it was a secondary amine, there's another CH3, or it could even be a C2H5. Now if, as I said, if I will expand it, what will the structure now be? It would be nitrogen overlapping with a carbon, which in turn is bonded to 3 other hydrogen atoms. Now just try and visualize this structure. Same way, if I have here, so this is overlapping with a carbon, which in turn is bonded to 3 other hydrogen atoms, CH3. Look at what is happening. There is crowding. They are going to push each other away. Bigger this particular alkyl group, more will be the repulsion, what we call as the bulky groups repelling each other. So bulky alkyl groups. Now because these bulky alkyl groups will repel each other, the bond angle may slightly increase, but it definitely does not reach the tetrahedral bond angle. So what we notice is, in the case of trimethylamine, CH3 whole thrice N, we notice that the bond angle is 108. So according to the structure of ammonia, the bond angle should be somewhere around 107 degrees. Tetrahedral bond angle is 109.8. In the case of amines, what happens is the bond angle, depending upon the size of the alkyl group, could be a little bigger than the standard bond angle in the case of ammonia. So remember that the structure is no longer tetrahedral, it's still a pyramidal structure. I will leave it on the screen for you to take down the notes, please. Go ahead, write it so that your notes are ready for offline reference when you are no longer watching the YouTube and preparing for your exams. In the next video, we shall be talking about the difference in the carbon-nitrogen bond length in the case of alkyl amines and aryl amines. There's a lot coming, and we shall be doing a lot of important and interesting things, so stay tuned for part 3. See you in the next video.